An experimental bicycle wheel is placed on a test stand so it is free to turn on its axle. If a constant net torque of 5 Newton meters is applied for 2 seconds, the angular speed increases from 0 to 100 revolutions. The net external torque is then removed and the wheel is brought to rest by friction in its bearings at 1.25 seconds. Compute the following: the rotational inertia, the frictional torque, and the number of revolutions made in the 125-second interval. Alright, so let's kind of look at this a couple different ways. First and foremost, part A, find the inertia. So they want to know what I is in part A. We're looking for I in part A, and we are given the torque. Now, the interesting part about this 5 Newton meters is no one says really where it's exerted. So, for all we know, it's probably exerted on the outside. There might be a chain involved, but it's not there. But we just know that it's essentially causing this to change its angular speed from 0 revolutions per second or per minute to 100 revolutions per minute. And it doesn't say what direction, so I'm just going to say it's going this way. Now, we know it's changing, so if I look at my velocities, we're going to have an angular acceleration going in this direction. Alright, now, again, the question becomes, what ideas do we use? Well, if we look at this in terms of linear equivalence, our linear equivalent for torque would be force. Our linear equivalent for inertia would be mass. Okay, if we look at what we're given here, we're given the initial speed, the final speed, and the time. Implied in this is also the acceleration. Okay, so looking at this carefully, we can actually approach this two different ways. We can look at this in terms of Newton's second law, forces divided by mass is equal to acceleration, or we can look at this in terms of impulse and momentum. Force exerted over a period of time will cause a change in angular momentum. Both will get you the same exact answer. I'm going to use Newton's second law of rotation because if we look a little bit later on in the question, they are asking for the number of revolutions made. So if they're asking for the number of revolutions made in part C, they're essentially asking for delta theta, which means I'm probably going to have to use my motion equations. So the acceleration will be helpful to have when I get down to part C. Alright, so let's move ahead here. Now, I have this in Newton meters, so I'm going to use Newton's second law of rotation. So I have the net torque over the inertia is equal to the angular acceleration. Alright, looking at this, I need to solve for I, so this would be the net torque over alpha is equal to I. Now to get alpha, we're going to have to do a little legwork here. So we know the initial and final angular speed. Well, first off, there are revolutions per minute. Now, especially since I'm dividing the angular torque by the angular acceleration, this is going to need to be in radians per second. They're all SI base units, so we'll end up with the proper units for inertia, which will be kg times meter squared. Alright, so the first step here is to convert the 100 revolutions per second, or excuse me, 100 revolutions per minute into a radian value. So I'm going to have 1 revolution over 2 pi radians, 1 minute over 60 seconds. Okay, we are going to get 200 pi radians divided by 60 seconds, or if you calculate that, it is 10.47 radians per second. Alright, that being said, we need to figure out what the angular acceleration is before we continue on. So we know the angular acceleration is the change in angular speed divided by the change in divided by the change in time. going to have the final velocity be 10.4 radians per second minus 0 radians per second, all divided by 2 seconds. Alright, when we solve for the angular acceleration, we get 5.235 radians per second, or radians per second squared. Okay, now if I come over here, I have 5 Newton meters divided by 5.235 radians per second squared. When I solve for the angular or the rotational inertia, I get 0.995 kg meter squared. Alright, so this is what my rotational inertia value would be. Oops. Okay, part B, find the frictional torque. Alright, so this thing's now spinning at 100 revolutions per second, and then after 125 seconds comes back to rest. Okay, so they're asking for what the frictional torque is. They literally just want to know what the torque is. So we're going to rearrange this to solve for torque of friction is equal to I times alpha. Alright, well, we just solved for what I is, and now we need to figure out alpha in this new situation. So this will equal I times the change in velocity. So if we're looking at this, our final angular velocity is going to be 0 radians per second minus the 10.47 radians per second. That would be the speed after 2 seconds. But this is all going to occur over a 125 second time interval. Okay. So all that being said, this 0 minus 10.47 radians per second divided by 125 seconds will give us the acceleration during the time it takes the wheel to come to rest, and then we can solve for the number of revolutions made by the wheel on a 125 second time interval. Okay, if we substitute all our numbers in, we're going to get 0.955 kg meters squared times 0.084, that will be a negative value by the way, radians per second squared. Okay, multiplying through, we're going to get negative 0.08 Newton meters, and this would be our frictional torque. There's your answer to B. Alright, now C. C that's for the number of revolutions made by the 125 second time interval, during the 125 second time interval. Alright, so we have to go back and we have to look at this in terms of a motion problem. Alright, we're given the final angular speed, the initial angular speed. We solve for the acceleration over the 125 second time interval, so we can go back and work this out. Probably given the initial and final and the acceleration and the time, we really can use any of them, but I'm going to use the change in angular displacement divided by, multiplied by the initial angular speed times time plus 1/2 alpha delta t. Okay, when you substitute everything in here, you get 10.47 radians per second times 125 seconds, okay, plus 1/2 times negative 0.084 radians per second squared times 125 seconds squared. Fix that plus sign. I don't even know what that looks like at this point. Alright. Okay, if you calculate all this, you're going to get 653 radians. Okay, to go from radians to revolutions, we use conversion factor. We know that there are 2 pi radians in 1 revolution, and if we calculate this out, we get 1.0398, or 104 revolutions. Alright, there's your answer.